Hi everyone, my name is Itai Kalev, and this talk is about unbalanced expanders for multiplicity codes. This is a joint work with Amnon Tashma, and let's begin. Now, firstly, we must define what is a condenser, because this is the main object we are going to construct in this talk. So a condenser is a function with two inputs, a k source of length n and a seed of length d. And what if this function needs to do in order to be a condenser is that the output distribution must be epsilon close to a k tag source of length n. Intuitively, what a condenser tries to do is to take the k source of length n and condense it into a smaller world of size only m, while maintaining as much of the mean entropy as possible. And to do so, it uses the uniform seed which it is given. Now, a condenser has three main parameters which we are interested in. The seed length, obviously the less the better. We don't want to give it more randomness than necessary. The entropy loss, k plus d minus k tag, which measures how much of the entropy we lose in this process. And when this is zero, we call the condenser lossless. And finally, the entropy gap, m minus k tag, which measures how dense is the output random variable in its world. And when this is zero, the condenser is just an extractor. Now, condensers are an essential building block in state-of-the-art extractor constructions and also have applications to storing stuff, and therefore we wish to construct them. And as with all pseudorandom objects, there are great non-explicit constructions, but for their users, we must construct an explicit ones, and this is what we will do in this talk. Now, to do so, we first need to talk about a connection between lossless condensers and bipartite expanders. So, a bipartite expander is a bipartite graph, with n left vertices, m right vertices, and left side degree d, and it is a Ka expander if for every set of left vertices of cardinality k, the set of all its neighbors has cardinality at least k times a. And in 2001, it has been discovered by Tashma, Umans, and Zuckerman that condensers, lossless condensers, and bipartite expanders are essentially equivalent, because a function is an nk to mk plus d condenser, that is a lossless condenser, with error epsilon, if and only if the corresponding bipartite graph to it is a 2 to the k 1 minus epsilon 2 to the d expander. With that in mind, we are ready to see our construction, but before we do so, let's first look at the GOV construction, as it is a very similar construction to ours. So let E be an irreducible polynomial of degree n, and let F be the field we receive when taking the ring of polynomial modulo this irreducible polynomial. And note that we can identify the elements of this field with polynomials of degree less than n, and also let h be a parameter. Now the GOV bipartite expander is defined as follows: CPV Fy is y, f of y, f to the power of h of y, and so forth up until f to the power of h to the power of m minus 1 y, where all the multiplications are in the field f, and we are using constantly the identification between elements of this field f and polynomials of degrees less than n. Now note that this construction is based on Parvesh-Vardy codes, which are codes with very good list decoding radius, and this construction can be viewed in the following way: f and y, the white neighbor of f, is connected to the white coordinate of the encoding of f under Parvesh-Vardy codes. Let's now move to the proof of the GOV construction, as our proof is very similar in structure, and it will be interesting to see where they do differ. So to do so, let's talk about the list decoding perspective of expansion. So the list decoding perspective is kind of opposite to the definition. If in the definition we take a set of left vertices and wish to show that it expands to the right, here what we wish to do is to take a set of right vertices and show that its list size is small, where the list size is the set of all, where the list of some set of right vertices is the set of all left vertices whose all its neighbors fall into the set T. And the simple lemma tells us that gamma is a Ka expander if and only if, for every set of right vertices of cardinality less than Ak, the size of the list of T is at most K, or actually less than K. With that in mind, let's look at the GUV expansion theorem. The graph CPV is expanding for every set of size less than K max by a factor of A, where K max is h to the m and A equals Q minus NMH. So now let's consider the proof. And the proof uses obviously the list decoding approach in combination with the polynomial method. So we let T be a set of right vertices of size less than AK max. We let Q be a non-zero polynomial that vanishes on T. And after that, we argue that every polynomial in the list is actually a root to the univariate polynomial Q star Z, where Q star Z is just the polynomial Q, where we substitute instead of y to the yi, z to the power of h to the power of I. And this is a polynomial in the field f in the variable z. So y is just a constant in this field. And after getting that step, we get that due to the Schwarz-Zippel lemma, the size of the list of T is at most the degree of Q star, which turns out to be h to the m minus 1, which is smaller than K max, as desired. Now, after seeing this construction, our construction should be very intuitive. Our construction is analogous to the GUV one, but instead of Parvallo-Schwarz codes, we use multiplicity Reed-Solomon codes. That is, the white neighbor of f is the white coordinate in the encoding of f under multiplicity Reed-Solomon code, which is just y, f of y, f to the first derivative at y, and so forth up to the mth derivative. This is also a good time to introduce the notation of dfx. Dfx is the infinitely long vector of x, f to the first derivative at x, f second derivative at x, and so forth up to infinity. Now note that our expansion theorem is very similar to the one for the GUV graph. And it says that our graph is expanding by a factor of A for every set of size smaller than K max, where A equals to Q minus the m plus second root of Q divided by 2 times NMH. So our expansion factor is very similar to the GUV one, with the only difference being this factor. And H is the m plus second root of K max, which is very similar to what we had in the GUV one. But here we need to state it as H is not a part of our construction, but only appears in the analysis. So now let's try and prove this theorem, and what we wish to do is to follow a similar path to the GUV one. We let T be a set of right vertices of size at most K max. We let Q be a non-zero polynomial that vanishes on T. And now, using a degree argument, we prove that every f in the list of T, for every f in the list of T, it holds that the Q, when substituting into yi, the ith derivative of f, is just the zero polynomial. And it can be written equivalently as Q composition with df equals 0. And now the final part is just to bound the number of solutions to the differential equation Q. But unfortunately, it's not that simple, as note that if we don't put any restriction on the solutions we are looking for, the number of solutions to an ODE may be huge, as for example, every polynomial of degree less than m is a solution to the differential equation, the nth derivative of f equals 0. But not all hope is lost, as we are only interested in solutions which appear in the list of t. Now it may seem like we went a full circle around and returned to our initial conditions, but this is not exactly the case because we do have the new ODE that we didn't have before, and we will now see how to use it. To do so, let's consider this subgoal. We let alpha b be an element of t, and what we are trying to do is to look for all elements, all neighbors of alpha b, which are part of the list of t. That is, if we are looking at the picture, we are looking for the green neighbors, but not interested in the blue neighbors, as they are although they are neighbors of alpha b, they are outside the list of t, and thus we are not interested in them. Now let's consider this new subgoal, and note that every such f which is in the list and also a neighbor of alpha b must have the following two properties. First, as it is a part of the list, it must be a solution to the differential equation q. Secondly, it must hold that CMRS f alpha equals alpha b, as f is a neighbor of alpha b. And explicitly, it means that f of alpha equals b0, f first derivative of alpha equals b1, and so forth up until the nth derivative. Now we are in a much better situation than we've been before, because now we're not only having differential equation, we also have initial condition on the solution. And therefore, we have here an initial value problem, which in general have only one solution, which is good for us. So what I'm planning to do for the rest of this talk is to talk about this in general statement, formalize it, and then prove it. I wish to do it with in an intuitive way. And to do so, I will need some notations and definition, but I wish also to introduce them intuitively. So let us consider this explicit differential equation, and what I'm asking is what will be its derivative with respect to x. Now, if you would think about it a bit, I'm guessing that most of you will get to the same answer. Therefore, we understand that there is an intuitive definition of deriving a differential equation, which we all agree on. Okay, and note that if f is a solution to the original differential equation, then it is also a solution to the differentiated one. And formally, this happens because if q composed with df equals 0, then also the derivative of q composed with df equals 0. But note that in order to derive q composed with df, we must have an explicit f. Yet here we were able to do it implicitly without having an explicit f. And this idea is formalized with this following definition/existence claim, which says that given q, a polynomial, which we will think of as our differential equation, there exists a unique polynomial, qj, such that for every f, q composition with df jth derivative is the same thing as qj composed with df. And this is exactly what we did here. If I will write this differential equation in polynomial form, then its derivative is just this differential equation in polynomial form. So this definition captures this intuitive idea. Now, interestingly, the polynomials qj have a very unique structure, which is qj can be written as dq to dyn times ym plus j plus some polynomial which is completely independent of ym plus j. And in this context, we call the coefficient of ym plus j, which is, as I said, dq to dym, the separand of q, and we write it as s subscript q. And the reason that the separand of q gets its unique name is will be clear in a bit. Let's substitute into this Qj and into this structure df hat with alpha. And note that on the one hand, because f is a solution to the differential equation q, we get 0. But on the other hand, if we substitute everything into the structure, we note that the separand is dependent only on our initial conditions, because all these values, alpha, f of alpha, f to the first derivative of alpha, up to the nth derivative of f at alpha, they are all part of the initial condition, and therefore the separand is completely dependent on the initial condition. Okay, so we get the separand times the n plus jth derivative, plus rj, which is independent of the n plus jth derivative. And note that what we get here is that the n plus jth derivative of f at alpha is completely defined by all the previous derivatives, as long as the separand does not vanish on the initial condition. This leads to the following uniqueness theorems, which tell us that given a differential equation q and an initial condition alpha b, if the separand does not vanish and the initial condition, then there is at most one solution to the differential equation which satisfies the initial conditions. And the proof of this theorem is exactly what we saw before. The n plus jth derivative at alpha can be uniquely determined from all the previous derivatives, and therefore we can get the n plus first derivative from the initial condition, the n plus second, and the n plus third, and so forth, until we get the entirety of f. So let's return to the condenser, or to our sub-goal. What we said we wanted to do is to bound the number of neighbors of alpha b from the list, and we kind of solved it. Okay, unless the separand vanishes at alpha b, there is at most one neighbor, which is great. Now let's go one step further, one step backwards. We wanted to bound the number of solutions to the differential equation which are in the list. And an idea to do so is to just iterate over every alpha b in T for which the separand does not vanish and generate its unique neighbor. And that way we will get a bound of size of T on the list. But the problem is obviously, what do we do with all the initial conditions, all the elements of T for which the separand does vanishes? One option is to ignore them, but this seems fishy and probably shouldn't work, and in fact it wouldn't work. But let's be explicit about why does it fail. Well, it fails if there is a function f which is in the list of T, but all its neighbors the separand vanishes on. And explicitly what this means is that SQ, the separand, vanishes on CMRS fx for every x in fq. Or in other words, the separands composed with the f equals 0 for every x in fq. But this means that f is actually a solution to a lower degree differential equation. We can think of the separand of q as a new differential equation, and what we got here is that f is a solution to it. And therefore, we can solve our problem by just recurse on the separand. That is, we work first on q, then on the separand of q, then the separand of the separand of q, and so forth. So let's now look at the full algorithm. The input of the algorithm is q, the differential equation, and the set t. And what we wish to do is to find all the solution of the differential equation q, which are part of the list of t. And what the algorithm does is to split t into two sets, t1 and t0. t1 is all the elements on which the separand does not vanishes, and each of those elements we can use to reconstruct a unique element due to the uniqueness theorem. And that's what we do, and call those elements L1. And with the second set is T0, all the sets on which the separand does vanishes. And what we do with them is we just call the algorithm with recursion on the differential equation the separand and the set t being t0, and we get a second list L0, and then we just return the union of them. And this algorithm exactly solved our problem. Now the only remaining question is what is the size of the return list of the algorithm, and note that every element of t generates at most one element in the return list, and therefore the return list size of the algorithm is at most the size of t. But we can do a tighter analysis and get a better bound by considering when two different elements of t generates the same generate the same solution to the differential equation. And using this tighter analysis, which I will not get into here, we get that the size of the return list is at most the size of t divided by q minus the weighted degree of the polynomial q. And this produces our expansion theorem for our construction. So let's conclude the talk. We obtain an explicit bipartite expander with very similar parameters to the GUV ones, and due to the connection between bipartite expanders and lossless condenser, we also get a lossless condensers with exactly the same parameters as the GUV one, or not exactly, but very similar parameters. Secondly, both the construction and the proof are very elementary. And the remaining question is obviously, can the given construction be improved into better than the state-of-the-art condenser? And thank you for listening.